right, welcome ladies and gentlemen. This is video number 2 in our matter unit, so you will need your notes open to the video number 2 section. You might also need your reference table for this, so you want to get your reference table out. In this video I'm going to be talking about mixtures, specifically 2 types of mixtures, and also percent composition. So what is a mixture? A mixture is a blend or a mix, obviously, of 2 or more substances. So this is a big idea, that you take these 2 substances, so you take an element in a compound, or you take 2 compounds, or you take 2 elements, and you simply blend them together. But this process, this blending process, this is really, really huge. This is a physical change only. No new substances are formed. You're not making anything new. You are literally just putting all the kids in the same pool, and that is it. The kids are not combining, they're not changing into different kids. The children are staying exactly the same, they're just all in the same pool together. Which means that mixtures can be separated by physical changes, physical techniques. So you cannot separate a compound by physical change. You cannot change an element by physical change, but you can take a mixture and change it and separate it using a physical process. The substances in a mixture are not connected chemically to one another in any way, shape, or form. They are not. If again, sand is a mixture. The particles in sand that are different, they are not actually bonded. They're not connected to one another. They're just all mixed together. So they are not bonded. Now, classic examples of mixtures: air, steel, dirt, brass, vegetable soup. This is always a big one. I think you can really picture, like with vegetable soup, all the different components. They're not actually connected because you got your carrots, you got your beans, you got your broth. They're all different, but they're not actually connected. Cereal, that's always a big one. Think Lucky Charms, the different components of that. That's very much a mixture. But the big one that students always tend to forget about is this one right here: air. 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 Air is a mixture. It is not a pure substance. The air in one place is not the same as the air in another place. It is different. Air is a mixture of things that are not actually bonded to one another. It is not a substance. It is not pure. It is a mixture. You've got oxygen, you've got nitrogen, you've got trace amounts of carbon dioxide and water, and then you have whatever else happens to be in the air. Smog, pollution, pollen, things like that. Air is a mixture. It is not a pure substance. That's one that the Regents will ask you about frequently, and a lot of kids tend to get tripped up in it. You think it's a compound. No, it isn't. It's a mixture. There are 2 types of mixtures: heterogeneous and homogeneous, and we're going to talk about both of them. So a heterogeneous mixture, well, the prefix hetero literally means different. So a heterogeneous mixture is what you can think of as an unevenly mixed mixture, meaning it has a different, there's our different, right, different for hetero, different composition in different places in the mixture. It's not evenly mixed. You can see usually the different components of the mixture. It is not a well-mixed mixture. Examples of a heterogeneous mixture would be things like salad. Salad is a great example of a heterogeneous mixture because it's not all the same. You don't look at your salad and it doesn't all look exactly identical. You can see, oh, well, over here we have tomatoes, and over here we have a large component of arugula, and over here we've got croutons, and you can literally see the different bits of it. It's not evenly mixed. Every single bite is not the same as another. Chicken noodle soup is also a heterogeneous mixture because with every spoonful you're likely to get different things. You can see the different components of the mixture. Most cereals, most salad dressings, any time where you can see that it's not a perfectly evenly mixed mixture, that is a heterogeneous mixture. Now, in terms of composition, this definition right here is really important. It's not a uniform composition, meaning the components are not the same throughout the mixture. Again, that goes to that difference bit. versus a homogeneous mixture. Now, it is still a mixture, so it's two or more substances, but the prefix homo means the same. That's literally what the prefix means. So this is now a mixture. So again, it's a mixture, so we do have two or more components, two or more parts to it. But in this mixture now, you have the exact same, that's our same, that's why it starts with homo, the same composition, the same distribution throughout the mixture. One sample of the mixture will be exactly the same as another. It is a very, very well mixed mixture. It is still a mixture, it's still two or more things, but it is an evenly mixed mixture. An example of homogeneous mixtures. Salt water is a great example of a homogeneous mixture, because if you were to look at a container that has salt water in it, you could not visibly see the difference. You can't like point over here, well, all the salt's over here and all the water's over here. No, it's evenly mixed. That means that every portion of that mixture, the composition is exactly the same as another portion. It's the same, prefix homo. Chlorinated water, and that would be another example of a homogeneous mixture. If you take your pool water, right, one sample of it should be exactly the same as another sample. But the big point here, anything dissolved in water is actually automatically a homogeneous mixture. That process of dissolving stuff in water actually makes it very evenly mixed. Vinegar is another example of a homogeneous mixture. The vinegar that you buy at the store, it is a mixture. It's a mixture of acetic acid. That's actually what makes it the vinegar bit, but it's diluted down. It's mixed with water. So again, you combine it with water, you made a very, 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 very evenly mixed mixture. Particle diagrams for both types of mixtures. So with a particle diagram for a mixture, you would need at least two or more different components. Because a mixture is two or more substances combined. And again, they're not touching, right? They're not physically, they're not chemically combined. They're not chemically connected, but you've got to have at least two things in them. A homogeneous mixture might look something like this versus a heterogeneous mixture might look like that. Now notice that in each of these, I do in fact have two different components. I have the green and the purple, but so that's what makes it the mixture. That's enough to make it a mixture. However, if you look at the homogeneous mixture, and I were to look at like this bit right here. Now notice in this bit I've got two purples and two greens, and then I were to take another bit right here, two purples, two greens, and then take another bit right here, two purples, two greens. I have the exact same composition throughout the mixture. It's uniform. Uniform composition. It's the same throughout. That's that prefix homo, meaning the same. Versus if I look at the heterogeneous mixture and I look at this bit right here and I've got four purples, and then I look at this bit right here and I've got two purples, two greens, and then I look at this bit and I've got four greens, it is not the same throughout. It is very much different, right? We have this different composition throughout the mixture. And that's what makes it heterogeneous, that prefix hetero. Percent composition, well, we're talking about composition. If you look at the back of your reference table, table T, you'll notice that there's actually a formula for percent composition. This is a big one for us. We use percent composition a lot in chemistry. But the nice thing is that percent is something you're already familiar with. And it's the exact same thing that you've seen before. It's part divided by whole multiplied by 100. The times 100 is what makes it a percent. Otherwise, the composition bit is the part over whole. So the way that we can use this, for example, in chemistry, is if we take this example right here that has 7 grams of sand and 13 grams of water, you combine them. Now this is a mixture because they're not chemically connected. So we have two components. We have sand and we have water. We know this would be a part. This would also be a part. And when you combine them and you get the whole, you have this sand and water mixture, right? This is the whole thing. By the way, this is a heterogeneous mixture because it is not evenly mixed. You can see the separate components. And we can calculate actually the percent composition of sand in the mixture because, again, this is our mixture right here, right? This is our whole thing. So this would go on the, so that is our whole. So we have part over whole times 100. And if we're looking for the percent composition of sand, that's the part that we're interested in the mixture. That's the whole. So we could simply do the part, which is the 7 grams of sand, divided by the whole, which is the 20 grams of the mixture, times 100. And whatever that works out to be, right? That's going to be 35%. And then lastly, the really big point about mixtures and percent compositions. Mixtures do not have fixed formulas, so they vary in their compositions. For example, you can get milk in different percentages. Milk is a mixture, right? You can get whole milk, you can get 2% milk, you can get 1% milk, you can get skim milk. You can get different concentrations of vinegar at the store. You can get different concentrations of like rubbing alcohol at the store. You can get like 70% rubbing alcohol, you can get 90% rubbing alcohol. These are mixtures. Versus elements and compounds, they have fixed compositions. They cannot vary. So they always have the same percent composition. This is not the case in mixtures. Mixtures can have different percent compositions. And these are just some examples of that. Different percentages of rubbing alcohols. This is proof that there are mixtures. They can change, right? That you have 30% rubbing alcohol, 70%, 90%. They're all mixtures, but they have different amounts in each one, and then you simply blend them together. That is not the case if you just had a pure alcohol that isn't mixed with water. It would always be consistently the same percent, same composition.